Good day, my name is Juan Sepulveda. I'm a PhD student in Aalborg University. This presentation will be about reliability analysis techniques. The presentation outline is shown here in the screen. First, we will see an introduction to deterministic design, probabilistic design, and variable transformation. Then we will take a look to different reliability analysis techniques like form, SORM, Crude Monte Carlo simulation, importance sampling, and asymptotic sampling. So for a deterministic design, let's imagine that we have a beam of length L, and we have a load applied in the middle of value P. Then we're going to observe a deformation or deflection in the middle. We will call this deformation XD. Then when we want to design this beam, the dimensions or whatever, we want to try to limit this deformation to a value XD critical or XD-CR. So our limit state function will be given by this expression G, which is 1 minus the deformation that we observe divided by the threshold level. So every time G is below 0, we're gonna say that it's a failure. Then we know from structure analysis that the deformation in the middle of the beam will be given by the load applied divided by the stiffness of the degree of freedom, D, which is given by the expression here in the right. Then using these two expressions into the limit state function, we can obtain something like the expression shown in the last line. And then when we replace the data, the numerical data, into this expression, we can obtain, for example, that the value B, in order to satisfy our design requirement, needs to be larger than 0.23. So now let's imagine that instead a fixed value of 100,000 for the load, this load now is modeled as a random variable. It means that have a mean is modeled by a normal distribution with mean value exactly the same than the deterministic design, but now have a standard deviation of 5,000, which is equivalent to a coefficient of variation of 5%. So now the load not only can take the value that we shown before, can always be larger or smaller than that. So now which value we will take in order to design our beam is not so clear as before. And here I'm going to make a small parenthesis regarding the variable transformations. Every time that we have a random variable which is not standard normal distributed, it's convenient to use a standard normal random variable. So here we can perform a transformation and say that the value of P will be expressed as the set times sigma P, which is the standard deviation, in this case equal to 5,000, plus the mean value or the expected value, which is 100,000. And in this case, set will be a standard normal random variables. This is convenient because many of the techniques that we will see in the future, they require that the random variables are standard normal random variables. So in the probabilistic design, the failure probability will be given by this expression shown here. So the failure probability will be the probability that the limit state function is below 0, which is equivalent to the integral of Q over the failure domain. Q is the joint probability density function of the random variables, and F will denote the failure domain or failure region, which is a subset in the parameter space of set. So now coming back to our example and using the expression that we found for the failure probability, we have that the failure probability is the probability that the limit state function is below zero, and which is equivalent to the integral of the probability distribution over the failure domain. Now we are not using anymore the probability distribution of P, we are using the probability distribution of Z that we saw that they are equivalent, right? So now we're plotting Z instead this probability distribution of P, which was the original. So now we need to identify which is the failure domain, and for example using the value of our deterministic design, which was B equal to 0.23, we find out that every time that we are below 0 in the limit state function, which is shown in the right y-axis, we are in the failure domain. So basically this integral is equivalent to calculate the area under the probability distribution in the failure domain. So to identify the failure domain, basically we need to go here in 0, from 0, intersect this curve, and then everything below, or which is equivalent to the right, will be our failure domain. So basically the area, the red area shown here, which is exactly the same than the probability, failure probability, will be 0.242. So continuing with our example, the design requirement now is the target reliability of the system, which is given by this expression, which is R star equal to 1 minus the target failure probability, or equivalently we can also say that our design requirement will be the target failure probability. So in case our target failure probability is 10 to the minus 4, for example, we can realize which is the value of B satisfying this requirement. And of course, every time that the value of B is smaller, our failure probability will increase, and every time that the value of B is larger, our failure probability will decrease, or which is equivalent, the reliability of the system will increase. So now we can imagine that we have a bit of more complexity into the problem. So now we can have, for example, two random variables instead only one, which will be the load, but also the Young modulus of the beam. And the probabilistic model of these random variables will be given by this table here. Both are normal distributed and with different mean values, of course, and also two different coefficients of variation. So now we will have two random variables, which will be Z1 related to P and Z2 related to E. Again, Z1 and 2 are standard normal distributed random variables. So now instead calculating an area, now what will represent the failure probability will be a volume in the failure domain. So if we plot, for example, for a given value of P equal to 0.26, which was satisfying 10 to the minus 4 as a failure probability, if we plot it into a xy axis, we can see that the safe domain is when g of z is larger than 0, will be given here in yellow, and our failure domain will be this in blue. So now we need to calculate the volume of this we need to calculate this volume in order to calculate the failure probability. So the question now is how to calculate it. So the first order reliability method, or so-called form, in form, the failure domain is approximated by a linear half space. It means that instead of having this failure domain that we can see have a curvature, we basically going to assume that is limited by a linear half space. And the design point is the point in F1 with minimal distance to the origin, which is equivalent to the minimal Euclidean norm. And the maximum of the PDF in F1 will be at the design point. So basically what we need to calculate is this distance, which is equivalent this beta value. So once we calculate the design point, or this distance to the failure domain from the origin, which is the minimal distance, the approximation will be given by this expression shown here, which basically we need to evaluate the cumulative distribution function of the standard normal distribution in minus beta. And this approximation is not approximation, it's exact when the limit state function is linear with respect to the vector of random variable set, and when set is Gaussian distributed. So for the case of b equal to 0.26, the approximation gives a failure probability of 1.22%. So the whole problem of a form is reduced to determine beta. So there is an algorithm that is shown here in 5 steps. So first we're gonna guess the initial value for the random variables. Then we want to calculate the limit state function. Then we want to calculate also the gradient of this limit state function. And then we want to calculate an improved guess of beta with this expression shown here. Then we're going to calculate the beta value as the expression shown in the point 4. And we're going to compare to the previous value. And every time that we don't observe any variation, then we're going to stop. In other cases, we're going to start or continue iterating until we reach our tolerance. So the advantages of form, one of the main advantages is that the estimator doesn't depend on the order of PF, and under particular conditions leads to the exact solution. The disadvantages is that the linearization introduces an error in the failure probability estimation. It is found that it's not accurate in high dimensions, and it is necessary to find the design point, which in high dimensions might be expensive, computationally talking. The second order reliability method, or so-called SORM, intends to improve form taking into account the curvature of the space of the limit state function at the design point, and the failure boundary is approximated by a hyperparaboloid with limit state function g2. So instead of having a linear approximation of the failure domain, now we have a curvature here also. So it's a bit more accurate in that sense. So the SORM approximation is given by this expression shown here, and of course the first part of this expression corresponds to the form solution, but now SORM put an additional terms in the right, where Ci are the principal curvatures of the paraboloid at the design point. It's also assumed that minus Ci is lower than 1 divided by beta for all variables. The next technique is crude Monte Carlo simulation. In order to understand better, I will show a small example on how to calculate the area of a circle and implicitly P. So let's imagine we have this quarter of an area of a circle. So what we will do here is simulate n random numbers into a unit square with area A equal to 1, which is this square here. Then we're going to draw a quarter of a unit radius circle with area P divided by 4. Then we're going to count the points inside the circle, n1, and then we're going to calculate the ratio. A1 divided by A should be equivalent to n1 divided by n. Then P will be given by the expression 4 times n1 divided by n. n1 again corresponds to the circle, to the points inside the circle, and n corresponds to the total number of points simulated. So the solution, of course, it will depend on how many points we simulate. It's not the same if we simulate 10 points or if we simulate a million, right? So here in this graph we can see how is affected the estimation of P by the number of simulations. So the true value of P is given by this red line, and in the x-axis here we can see how it converges when we start increasing the number of points. So then we can use exactly the same approach to calculate the volume that we wanted to calculate in order to estimate the failure probability. So a large number of n realizations of the random variables set of the random variables is simulated using the probability distribution, and the failure probability estimator PF is obtained by counting the number of realizations in the failure domain. So the procedure basically will be that we will simulate n realization of standard random variables, and this is the only step where the information regarding the distribution of the random variables is included. Then we're going to identify the number n1 of realizations in the failure domain, and this will be the only step where the information regarding the limit state function is included. Then the estimator will be given by n1 divided by n. So the failure probability will be basically the points in the failure domain divided by the total number of points simulated. So because we are simulating random numbers, every time we perform a crude Monte Carlo simulation analysis, we're going to obtain a totally different result. So in these lines here represent different runs of Monte Carlo simulation. So we can see that when we have around 20,000 samples, the failure probability we can see here that gives different values. But of course, when we increase the number of samples, we are converting to a unique value. So in our example, using beta b equal to 0.26, how n affects the variability of the estimator. So there is a well-known formula of the coefficient of variation of the estimator. So we put this formula into this table here. So for each value of n, given that our estimator gives us 1.24%, we have a coefficient of variation of the failure probability. So basically, let's say if we want to have a coefficient of variation below 10%, we will need at least 10,000 samples. So continuing with our example, using a value of b equal to 0.285, which is equivalent to say that the failure probability is 1.5. times 10 to the minus 4. How PF affects the coefficient of variation. So here we can see for different runs of Crude Monte Carlo simulation that before we have a pretty accurate value for 100,000 samples. Now, when the failure probability is lower because we are increasing this value, so it means that the failure probability will be smaller. As we can see here, it seems that there is not enough accuracy in our estimation. So then we will need to increase our number of samples up to 1 million in order to be below 10%, which is normally accepted. This of course depends on the discipline, but in structural engineering at least is the value that is normally accepted. So this is basically the main disadvantage of Crude Monte Carlo, that when the limit state function is far from the origin, it's more difficult to obtain realizations in the failure domain, as we can see here. When we have a p equal to 0.26, and this is the failure probability, we have several samples in the failure domain. But then when we change the value of p, and of course change the limit state function, it gets more far from the origin. It's more difficult to obtain samples in the failure domain. So the main advantage of Crude Monte Carlo simulation is that it's independent of the number of random variables. Also is independent of the shape of the limit state function, doesn't matter if it's linear or not, and the estimator is unbiased. But the main disadvantage is the fact that the number of samples required is proportional to 1 divided by the failure probability. So this is why importance sampling plays an important role. So the idea behind importance sampling is that we, instead simulating samples in the origin, we're going to simulate samples in the design point. So we're going to obtain much more samples in the failure domain, which will give us a much accurate solution. So our original integral to calculate the failure probability, we're going to slightly modify it, aggregating probability density function p. So now the samples will be drawn from p instead of q, and we will take into account this this movement, let's say, of the origin with this quotient here, q divided by p. But now remember that the samples will be drawn from p instead of q. So continuing with our example, using b equal to 0.285, we can see here in this table how the coefficient of variation of the estimator given by Monte Carlo simulation is much larger by the one given by importance sampling. So we can see that, for example, with 1000 samples in importance sampling, we already achieve the 10% of threshold of acceptance versus 258%. So basically, with 1000 samples achieves the same accuracy than 1 million samples using Crude Monte Carlo simulation. So the main advantage of importance sampling is that it reduces dramatically the number of samples required by using Crude Monte Carlo simulations. But the main disadvantage is that an incorrect selection of the importance sampling density function can lead to erroneous estimates of the reliability. And the last technique is called asymptotic sampling. And the idea is to use asymptotic properties with a simple regression technique. So Crude Monte Carlo simulation is used to estimate the failure probability in each support point. The standard deviation for each support point is increased by a factor y divided by f. And due to the larger standard deviation, the failure probability is increased, reducing the computational cost. And the functional form that we're going to use is given by this expression here. So basically, before, when we have the failure domain too far from the origin, for example, in this case, we don't have any simulation in the failure domain, any sample in the failure domain. But then when we use a standard deviation 1 divided by 0.6, when f is 0.6, we can see that we have samples in the failure domain. So what we're going to do basically is use different values of f and basically calculate the failure probability using Crude Monte Carlo simulation. And then we're going to take all these points. For example, we have 3 here, for example, and then we're going to try to perform a regression analysis using the functional form. And then what we're going to do is evaluate this functional form for f equal to 1, which is the original failure probability that we're trying to estimate. So here we can see this is not directly the failure probability, is beta divided by f, but it's totally equivalent. So if you perform a regression analysis, the following parameters were estimated of the functional form a, b, and c. And then when we evaluate for f equal to 1, we're going to obtain beta equal to 3.61. And the estimator then will be given by this expression here, 1.5 times 10 to the minus 4. And the original one was pretty much close to that. Maybe there is a difference in the decimals, but it's pretty much the same. So what's the main advantage of this technique is that the failure probabilities estimated here, here, and here are much larger than the original failure probability, which is here. So that implies a much lower computational cost. So that's my presentation. Thank you very much, and you can write me an email anytime to this address. Thank you very much.